You've built a system. It works well at low scale. You've tested it, monitored it, you understand its behavior. Then you scale up. More traffic, more instances, more containers. You add capacity everywhere the metrics tell you to. Database, scaled. Cache, scaled. Application tier, scaled. Still slower. You go through every component. Every one of them has headroom. Nothing is saturated. Nothing is throwing errors. Your infrastructure looks healthy by every measure you're watching. But the system is slower at 10 times the load than the numbers suggest it should be. What you haven't checked, what almost nobody checks, is whether the infrastructure keeping your workloads separated from each other is consuming the capacity you thought you were adding. Because isolation mechanisms are not passive. They are not walls that sit there doing nothing while your traffic flows past them. They are active software, running on the same hardware as your workload, consuming CPU, memory, and network processing for every packet, every connection, every process boundary they enforce. At low scale, that cost is invisible. At high scale, it can become the thing that's slowing you down. To understand why this happens, you need to think about what isolation actually does at runtime. When your cloud environment enforces isolation between workloads, it doesn't do it once at setup and then step back. It does it continuously for every operation that crosses a boundary. Every network packet entering or leaving a container is inspected against rules. Every system call from a process is evaluated against namespace permissions. Every connection attempt is checked against security group policies. This inspection isn't free. It runs on the same CPU that runs your application. It consumes the same memory bus. It competes for the same kernel resources. At 10 containers, this overhead is negligible. You'd never notice it. At 1,000 containers on the same host, or 100,000 packets per second through a heavily ruled network policy, the overhead accumulates. The isolation mechanism, the thing that was supposed to protect your workload, starts competing with your workload for the resources it needs to run. Think of a security checkpoint at an airport. One gate, low traffic. Every passenger gets checked thoroughly. Nobody waits. Same checkpoint. Peak holiday season. The queue backs up. The checks get faster and less thorough, and the checkpoint itself is now the thing causing delay. The security mechanism is still running. It's just degrading under a load it wasn't designed for at that scale. The isolation is still there. It just now costs more than you budgeted for. Let me make this concrete with 3 specific mechanisms where isolation overhead becomes a real performance problem at scale. The first is IP tables in Kubernetes. IP tables is the Linux kernel mechanism that enforces network rules, which traffic is allowed, which is blocked, which is redirected. In a Kubernetes cluster, every service, every network policy, and every pod routing rule translates into IP tables entries. In a small cluster, you might have a few hundred rules. In a large production cluster, hundreds of microservices, multiple namespaces, fine-grained network policies, you can easily have tens of thousands. Here's the problem. IP tables evaluates rules sequentially. Every packet traverses the entire rule list, top to bottom, until it finds a match. At 100 rules, this takes microseconds. At 50,000 rules, it takes significantly longer, and it happens for every packet on every node continuously. The result is CPU time spent in kernel space, not running your application, not processing your business logic, but evaluating isolation rules. On a busy node, this can represent 10 to 20% of total CPU capacity. Capacity that shows up in your provisioning numbers as available. Capacity that is actually consumed by the mechanism enforcing your network isolation. The system isn't broken. The rules are all correct. The isolation is working perfectly. It's just that at this scale, working perfectly has a cost that was invisible when you designed the system at 1/10 of the current load. The second is Linux Contract, connection tracking. Contract is the kernel subsystem that maintains a table of active network connections. It's what allows stateful firewall rules to work. It's what makes it possible to say, allow established connections, rather than having to explicitly permit every packet in both directions. Every active TCP connection has an entry in the contract table. The table has a maximum size. On a busy host running many containers with many concurrent connections, that table fills up. When it fills up, new connection attempts fail, not with a meaningful error, but with silent packet drops that look, from your application's perspective, exactly like intermittent network failures. The contract table is a resource consumed by the isolation mechanism. Your application never touches it directly. Your monitoring almost certainly doesn't watch it. But when it fills under load, your application's network behavior becomes unpredictable in ways that are extremely difficult to trace back to their cause. The third is security group evaluation under high connection churn. In AWS, security groups are evaluated at the hypervisor level for every new connection. At low connection rates, this evaluation is fast and the overhead is trivial. At high connection churn, microservices making thousands of short-lived connections per second, serverless functions spinning up and down rapidly, the evaluation frequency increases proportionally. The overhead doesn't show up as security group latency in any metric AWS exposes to you. It shows up as slightly elevated connection establishment times, slightly higher first byte latency, slightly increased variability in P99 response times, the kind of degradation that looks like application noise rather than infrastructure cost. All three of these mechanisms share the same underlying pattern. The isolation is working correctly. The cost of that correctness scales with load, and at sufficient load, the cost stops being a rounding error and starts being a budget item that nobody allocated. The reason isolation overhead is so consistently misdiagnosed is that it presents as generic slowness. Your CPU metrics show elevated usage, but the usage is in kernel space, not user space. Most engineers look at total CPU and assume their application is the consumer. Splitting CPU time into user space versus kernel space is not a default dashboard view in most monitoring setups. It requires explicit instrumentation. Your network latency metrics show increased P99, but the increase is in connection establishment, not in data transfer. Most latency monitoring measures end-to-end request time. Separating connection setup latency from transfer latency requires packet-level measurement that very few teams have in place. Your application logs show nothing unusual because the application is functioning correctly. It's the layer below the application that's degraded. This creates the same pattern that makes all infrastructure layer problems hard to find. The effects are visible at the application layer. The causes are invisible there. You need to be looking at the right layer: kernel CPU split, contract table utilization, network rule evaluation cost, to see what's actually happening. And these metrics are not where engineers look first, second, or usually third, when a scaling problem appears. The iptable's scaling problem in Kubernetes became severe enough that it drove a fundamental re-architecture of how network isolation is enforced at scale. The solution was eBPF, a technology that allows custom programs to run inside the Linux kernel, attached directly to network events, without traversing a sequential rule list. Instead of evaluating 50,000 iptables rules for every packet, an eBPF-based solution like Cilium attaches a small compiled program to the network interface that makes the routing decision in a single lookup. The isolation guarantees are identical. The cost at scale is orders of magnitude lower. The reason the industry moved to it wasn't that iptables was broken, it was that iptables was correct, but unaffordably expensive at the scale that production Kubernetes clusters had reached. This is the pattern that plays out whenever isolation mechanisms hit their scaling limits. The mechanism works. The cost grows. At some threshold, the cost forces a re-architecture of the mechanism itself, not the workload it protects. It also illustrates something worth sitting with. The cloud industry has repeatedly had to redesign its isolation mechanisms, not because they failed to provide isolation, but because providing isolation at scale turned out to be more expensive than originally assumed. That cost was always there. It just became visible at scale. There's an uncomfortable symmetry at the center of this problem. The mechanisms that protect your workload consume the same resources your workload needs to run. CPU, memory, network processing. The isolation layer and the application layer are drawing from the same pool. At low scale, the isolation layer's draw is negligible, At high scale, it's a real competitor. This doesn't mean isolation is optional. It means it isn't free, and that it works fine in staging is not the same claim as it will scale to production load. Staging is low scale. Production is where the overhead becomes visible. The engineers who understand this don't get surprised when a system that performed perfectly at 10% capacity starts behaving unexpectedly at 80%. They've already asked how much of their capacity budget is allocated to the mechanisms enforcing their boundaries, not just to the workloads those boundaries protect. That question sounds technical, but it's really a resource allocation question. And in cloud infrastructure, the answers only show up when you know where to look.